Okay, so tell me a little more about how lift and drag interact with airplanes and why should I care? How is this relevant?
All right. This is actually very relevant to how people fly airplanes. Um, a lot of people learn this almost by rote, but it's really important to know where this interrelationship comes from. So, to review, an airplane is under a variety of forces, one of which is its weight, right, which is gravity pulling down. The other is its lift, and the third is the drag that's pulling it backwards.
Okay.
And the fourth is the thrust, which we have kind of decided not to talk about too much, but it's basically the way the motor of the engine is pulling it of the airplane is pulling it forwards. And we also said that this drag breaks down into two kinds: parasite drag, which is caused by just the whole idea of how you can push a body through the air, and as it cleaves asunder the air and pushes it out of the way, it's going to get resistance from the air. And induced drag, which is the drag that we learned is produced by any lift generating object because of the centrifugal force on the little parcels of air being canted towards the back as they go around the curve. All right. So one of the questions you can ask yourself is, how much lift do we need? And in fact, let's give this some numbers, shall we? So let's say the weight of the airplane is 1,000 pounds, right? So I have a 1,000 pound airplane. At any one time while we're flying through the sky, how much lift do we need?
1,000 pounds?
Exactly. Regardless of how we are flying, if we are flying level, and we're just talking about flying level, going straight and level for now, we need to be producing 1,000 pounds of lift. Now, I said if we're flying level. Really what I'm trying to say is if we are not accelerating. But just think about it as steady state flight. Puttering along through the air, straight and level, just going without any changes. All right? Now, another fact you might think about is airplanes fly at different speeds. When I want to go from one place to the other and I'm really booking, I'm going to fly as fast as possible. When I'm about to land, I want to slow down because landing is really just a controlled impact with the ground, and I want to take that impact as slowly as possible. And at different times, I may choose yet different speeds at which to fly. So let's talk about the speed of the airplane and how that changes the way we generate lift. And remember, the speed of the airplane translates directly to the speed of the air parcels that are whooshing forward at me. Okay?
Mm-hmm.
So remember, I'm this imaginary airplane, and there are these air parcels coming at me.
Does the air actually divide itself into parcels?
It does not, but for the purposes of analysis, we can divide it into parcels and imagine each one individually. So if you wish, think about these parcels as being just part of the continuum of the air that extends everywhere, and we're just thinking about the air one parcel at a time. And let's say that I allow this parcel to rotate this much, right? And then it zooms off in this direction, and this is the angle whereby I allow the parcel to rotate while it's under my control. Got it?
Mm-hmm.
And let's say this is happening at 100 miles an hour, right? So as the air parcel comes right around and zooms over the top, it gives me a nice big oomph of lift, and then right here I let go of it, and life is all good. Okay?
Okay.
Now let's say I slow down to 50 miles an hour, right? Which is half of that. So now we're going to think about 50 miles per hour. What are the properties of the air parcels that are now of interest? Two things. First of all, each air parcel coming at me has half the speed, and therefore half the lift generating oomph of a 100 mile an hour air parcel. And if you want to get an idea of how that looks, here's our little water bucket again, right? I'm spinning it very, 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 very fast, and it's keeping the water up in the bucket really well. I'm going to spin it slower and slower, and as I go slower and slower, now there's not enough force. The bucket falls down over the top and spills out the water. So the slower this air parcel is going, the less oomph I can get out of it as it goes around the curve. That's number one. Number two, because I'm going half as fast, I encounter half as many air parcels per unit of time. It just makes sense. So now at 50 miles an hour, I have half as many parcels of air, each with half as much oomph. I'm getting 1/4 of the oomph that I had at 100 miles an hour. And oomph actually has a very specific physics representation. It is called dynamic pressure, or Q. But for now, just think about it in terms of just intuitive oomph, right? I have 1/4 of the oomph because I have half as much oomph per particle and half as many particles. But I still need 1,000 pounds of lift. How am I going to get that? I'm in trouble, right? Well, the only way I can get it is, instead of letting go of the air parcel over here, I have to hang on to that poor little air parcel for a lot longer and finally let go of it, let's say, around here. Okay? And so now, when I let go of it, it's actually moving at a larger angle than it was when it was in the previous setting. So what can we observe? First of all, I have created more circulation. And I'm not sure if I introduced the idea of circulation yet, but circulation is the process of bending the air and introducing a circular motion to it. And we create lift by creating circulation in the airstream. That is what we do when we grab onto it and make it go in a circle and use centrifugal force. We're adding circulation to the flow. To fly slower, I need more circulation. Furthermore, and this is crucial, notice the behavior of this air parcel as it interacts with me when I'm going slower. It spends more of its time around here, right? Around this angle, it spends more of its time pulling backwards harder. So I know that my lift is always at 1,000 pounds. When I was letting go of the parcels here, my drag, my induced drag, was some value like this, right? When I'm letting go of the parcels here, my induced drag is way higher. So the amount of drag I'm feeling to produce the same lift is higher when I'm going slower.
Okay.
All right, so let's plot that as a graph. And what we're going to build up is what is known as the drag curve of the airplane, right? I'm going to make myself some space on the board.
Am I getting a physics lesson here?
You might be. I'm sorry. So, this is the speed of the airplane. I'm going to call it V. And this is the drag on the airplane. I'm going to call it D. Right? Now, when I'm going really fast, I'm just skimming the little parcels over the top and letting them go. My drag is quite low. When I'm going slowly, my drag is huge because I'm grabbing onto these and letting them go only after a long time, and they're pulling back at me, so my drag is up here. And it turns out that the curve looks something like this. This is the induced drag. Okay? Now let's think about the so-called parasite drag. I have this airplane-shaped object here, and remember, we have parcels of air that this thing is colliding with. Remember the previous thing we said, that when we go half as fast, we're encountering half as many parcels, each traveling at half the speed, right? So the parasite drag of pushing this thing through the air is probably about, more or less, sorta, kinda, 1/4 as much. And in fact, the parasite drag is reduced quite drastically the slower you go. So let us draw the parasite drag on this curve right here. The parasite drag looks something like this. And this is parasite, right?
Okay.
Now the total drag on the airplane equals the parasite plus the induced drag, right? And so changing the units around a little bit, because we're rescaling a little bit for that. sorry about that. The sum of these two curves looks something like this, right? This is the total drag curve.
Okay.
And the interesting thing about that is that there is a minimum. There is a point where if you fly slower than that, your airplane encounters more drag. And if you fly faster, your airplane encounters more drag.
So, someone who actually never studied physics at all,
Yes.
how could you put this into just sort of intuitive language? I mean, for me, the graph just makes things more confusing.
It does?
Yeah.
Huh. Well, I think I would probably consider, like over here, you're flying and producing a huge amount of circulation, but you're also flying really slowly, so you're having a really easy time of going through the air.
Uh-huh.
And so here the amount of drag is huge, and over here you're flying really fast, so you're having a lot of effort beating through the air, and you're just producing a tiny bit of circulation, but because you're using a lot of effort to beat through the air, your drag is huge. But around here, you are beating through the air at a moderate speed, and you're producing a moderate amount of circulation. And so somehow or the other, these things combine to produce a moderate amount of total drag.
So that's where you want to be if you want to use less fuel and just be happy.
It turns out, with a very specific trick, the answer is yes. It turns out that the power required equals the drag times the speed. And so the power curve is yet another curve that looks a little bit different. And it lags towards here, and the minimum power is going to be a little bit slower than the minimum drag. So it turns out that if you want to fly the flattest possible trajectory relative to the air mass, you fly here, and if you want to fly for the longest time before you descend, then you fly here.
Okay.
If you want to use the smallest amount of gas per unit of time, you fly here. And this whole optimization fits into both what you use as a pilot to figure out how fast to go on a given trip, but also how you feel as a pilot, because your airplane feels completely different when you are so-called on the back side of the power curve.
How would it feel?
The slower you fly, the more your airplane mushes down and wants to descend. And it seems to you, as a person schooled in the physics of terrestrial beings, that going slower is safer. Because slower is better. You have less of a chance of bumping into stuff. But in this case, on the back side of the power curve, the slower you go, the more drag you need to overcome. You're going to need to either add more power by adding more gas to your engine, or you're going to descend faster.
So is it kind of like you need to pedal a little faster when you're biking, otherwise you tip?
That's very similar, yes. It is a phenomenon where your speed actually gives you stability, and the lack of speed creates instability and scariness. And that is one of the things that a pilot really needs to be able to internalize in every possible way. They need to learn it every way. The physics, the math, the intuition, the diagrams, the experience in the airplane. They just need to know this because this is the one counterintuitive thing about flying that we get trapped in.
Uh-huh.
Now the interesting thing about this though is that I was able to derive all of this without any reference to how airplanes actually work. This is a property of any lift-generating object which generates lift by bending the airflow. It must behave this way. How we accomplish that on actual airplanes, that's the topic for the next little bit.
Okay.